and welcome back to NEET Prep Go. So today we will be doing the entire revision of S block elements. So I had done this before in parts but did not get the opportunity to do the entire revision. So today we will be revising entire S block element. So without any further ado, let's get started. The first element of alkali and alkaline earth metals of group 1 and group 2, that is lithium and beryllium, it differs in many respects from the other members of the group. So both lithium and beryllium, they are the first elements of group 1 and group 2, that is respectively group 1 elements are called as alkali metals and group 2 elements are called as alkaline earth metals. They both show properties which are different than the other members of their group, therefore we can also call it as anomalous behavior. Okay, now the S block elements are in the periodic table are the elements in which the last electron enters the outermost s orbital. The s orbital can accommodate only 2 electrons. So therefore the two groups, group 1 and group 2, that are alkali metals and alkaline earth metals respectively, belong to the S block of the periodic table. The group 1 of the periodic table consists of lithium, sodium, potassium, rubidium, cesium and francium, and they are collectively known as alkali metals. Why are they collectively known as alkali metals? Because in reaction with water they give us alkaline hydroxides, that is they form hydroxides on reaction with water which are strongly alkaline in nature, therefore they are called as alkali metals. Group 2 elements are called as alkaline earth metals, which are the elements in group 2, that is beryllium, magnesium, calcium, strontium, barium and radium. They are respectively called as alkaline earth metals. Why are they called as alkaline earth metals? Because their oxides and hydroxides are alkaline in nature and they are found in the earth's crust. Now among the alkali metals, sodium and potassium have larger abundance, whereas lithium, rubidium, cesium have lesser abundances. Francium, that is an isotope of francium, is highly radioactive. The longest lived isotope of francium, that is francium 223, has a half-life of only 21 minutes. This is important to remember. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in the abundances, whereas rest all, that is beryllium, is rare, and strontium and barium also have lower abundances. Then radium is very rare, that is it only makes up 10 to the power 10% of igneous rocks. What are igneous rocks? That is when the lava, that is the molten magma, that is molten rock, when it becomes cool and hardened, then it forms igneous rocks. So radium only makes 10 to the power 10% of igneous rocks. The general electronic configuration of S block elements, that is noble gas, is NS1 for alkali metals, and first noble gas, that is you can say argon 18 for example, and then NS2 for alkaline earth metals. So NS1, NS2. Then lithium and beryllium are the first elements of group 1 and group 2. So we learned that the first elements of group 1 and group 2, that is alkali and alkaline earth metals respectively, they are lithium and beryllium, and these two show different properties than that of the other members of the group. So lithium and beryllium show anomalous properties. What are these anomalous behavior or anomalous properties? That is they resemble the second element of the following group. So lithium resembles lithium resembles magnesium and beryllium resembles aluminium. So they resemble the element, that is the second element of the following group. So that is of the following group, the one which is in the next group in the following period. So it is diagonal relationship basically. So lithium shows similarities to magnesium, whereas beryllium shows similarities to aluminium. See, like this. This is here. Lithium shows similarities to magnesium, and beryllium shows similarities to aluminium. So in the following period, as well as the following group and second to it, like next to it. So that is in the next group as well as in the next period. This type of diagonal similarity is commonly referred to as diagonal relationship in periodic table. The diagonal relationship is due to the similarity in ionic sizes or atomic charge radius ratio, that is charge by radius ratio of the elements. Monovalent potassium ion Na plus and monovalent sodium ion, that is sodium ion Na plus and potassium ion K plus, as well as divalent calcium ion Ca2 plus and divalent magnesium ion Mg2 plus. They are very important and are found in large proportions in our biological fluids. These ions perform important biological functions like what? Such as maintenance of ion balance and nerve impulse conduction. So these ions perform very important biological functions such as maintenance of ion balance, that is maintenance of ion balance and nerve impulse conduction. So they balance the they maintain or they balance the ions and they help in nerve impulse conduction. Now group 1 elements, alkali metal. The alkali metals show regular trends in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of alkali metals are discussed below. So first comes electronic configuration. We know that in electronic configuration, alkali metals have first a noble gas, then NS1 configuration outside the noble gas core. The loosely held S electron in the outermost valence shell of these electrons makes them most electropositive metals. Why are alkali metals or alkali elements or group 1 elements most electropositive metals? This is because they have only one valence electron outside their noble gas core, and this makes them the most electropositive metals. They readily lose this one electron to give monovalent ions, that is M+, and hence they are never found in free state in nature. They lose this one valence electron readily to give M+ monovalent ion, and therefore they are never found freely in nature. They are never found in free state in nature. The alkali metals are never found in free state in nature. Okay. Now lithium, sodium, potassium, rubidium, cesium, francium, that is you can see 1s2, 2s1, 1s2, 2s2, 2p6, then 3s1, then 4s1, then 5s1, then 6s1, then 7s1. Now atomic and ionic radii. The alkali metal atoms have the largest sizes in a particular period of the periodic table. That is the atomic and ionic radii. That is alkali metal have the largest sizes in a particular period, because we know that with the increasing period the nuclear charge increases. As the nuclear charge increases, the atomic and ionic radii decreases. Therefore, since this is the group 1, that is the first group, therefore the atomic and ionic radii are largest in alkali metals. Now monovalent ions M+ are smaller than the parent atom. Obviously, we also know that if you lose one electron, then your atomic radii becomes lesser. If you gain one electron, it becomes more, and if you are neutral, so M- is greater than M, which is a neutral, it is greater than M+, which is monovalent ion. Then atomic and ionic radii of alkali metals increases as we go down the group. Why? Because the shells keep getting added, and there is increase in size while going from lithium to cesium. Then comes ionization enthalpy. Ionization enthalpy of alkali metals are considerably low. Why are the ionization enthalpies of alkali metals considerably low? Because if they lose that one valence electron that they have, that they can readily lose, then they will attain a noble gas configuration. And therefore, since they have that one valence electron and they are the most electropositive metals, they are always ready to lose that one valence electron, and that one valence electron is not even that strongly attached to the nucleus. Therefore, they can easily lose that one valence electron. Hence, they do not need that much energy to lose that electron. Therefore, the ionization enthalpies of alkali metal are considerably low, and they decrease even further as we go down the group. Why? Because as we go down the group, the shells increase and the atomic radii also increases. Therefore, as compared to nuclear charge, the atomic radii increases even more. Therefore, the attraction of the outermost valence electron with the nucleus, it becomes lesser and lesser because of screening effect of shells coming between them. Hence, as we go down the group, the ionization enthalpy decreases even further. Now hydration enthalpy. Hydration enthalpy of alkali metal ions decreases with the increase in ionic size. As the hydration as the ionic size increases, the hydration enthalpy decreases. Always remember that hydration enthalpy is inversely proportional to the atomic size. So as the hydration enthalpy will increase, atomic size will decrease, and as the atomic size increases, hydration enthalpy will decrease. So lithium has the highest hydration enthalpy and cesium has the lowest hydration enthalpy. Lithium has maximum degree of hydration, and therefore lithium is the only element which can form hydrated salts. That is, it forms LiCl.2H2O. This is very important. Lithium forms LiCl.2H2O. Now physical properties. All the alkali metals are silvery white, they are soft and they are light metals. Because of their large size, they have relatively lower density, which increases down the group from lithium to cesium. The exception is sodium and potassium, in which sodium has lesser density than, potassium has lesser density than sodium. So in alkali metals, due to large atomic sizes, the density is low, but the density increases down the group from lithium to cesium. The only exception is that potassium is lighter than sodium. Now the melting points of alkali metals are low, indicating that there is weak metallic bonding due to the presence of only one single valence electron. So with little bit of heat, the valence electron can easily get excited. The alkali metals and their salts impart characteristic color to an oxidizing flame, and this is because the heat from the flame excites the outermost orbital electron, and this outermost orbital electron goes to a higher energy level, and when it comes back to the ground state, then there is obviously emission. We know that from higher to lower, when an electron comes, then there is emission, and when lower to higher it goes, then there is absorption. Therefore, when it comes back to the ground state, there is emission of radiation in the visible region, and we see that lithium gives crimson red. Then lithium gives crimson red. Sodium gives yellow, then potassium gives red, violet, rubidium gives red violet, and cesium gives blue color. And the wavelength is 670 for lithium. Then it decreases. That is, for sodium it is 589. That is then it is 766 for potassium. Then it is 780 for rubidium, and it is lowest for cesium, 455. Alkali metals can therefore be detected by the respective flame test, and they can be determined by flame photometry and atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed is sufficient to get the valence electron excited and make the atom lose an electron. And this property, in which the light energy gets absorbed and the electron can easily get excited, that is, and the atom loses an electron, this property makes cesium and potassium very good photoelectric cells, useful electrodes in photoelectric cells. Cesium and potassium, this is a very important point. Then atomic number, atomic mass, ionization enthalpy. Ionization enthalpy of lithium, that is, it decreases. It is decreasing. See, from lithium to sodium, potassium, rubidium, cesium, francium, it is decreasing. So it is constant. There are no exceptions. In hydration enthalpy, again the same. Hydration enthalpy decreases as the size increases. Then metallic radius also increases as we go down the group, as new shells start getting added. Then the radii also increases. Ionic radius also increases down the group. Now the melting point, boiling point, that is, the melting point of lithium is greater than sodium, which is greater than potassium, greater than rubidium, greater than cesium. So melting and boiling point also decreases down the group. For both melting and boiling point, both will decrease down the group. As more and more shells will get added, then the electron, that is metallic bonding, will become lesser and lesser. Therefore, with little bit of supply of heat, it will lose the electron. Density increases down the group, but the only exception is potassium and sodium potassium, in which even though it should increase down the group, the density of sodium is greater than the density of potassium. Standard potentials, then occurrence in lithosphere, which is represented in parts per million. Lithosphere is the Earth's outer layer, its crust, and the under part of the upper mantle. Okay. Now chemical properties. The alkali metals are highly reactive due to their large size and very low ionization enthalpy. They will easily lose the electron, and to do that, they are very reactive. That is, they are not stable basically. The reactivity of these metals increases down the group. This is also a very important line. The reactivity of the alkali metals increases down the group. Reactivity towards air. The alkali metal tarnish in dry air, that is, it is like rust, but it is not exactly rust, that is, they tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen, forming oxides. Lithium is the only one which forms monooxide, sodium forms peroxide, and the other metals form superoxide. The superoxide O2 minus ion is stable only in the presence of large cations, potassium, rubidium, and cesium. So, lithium is the only one which forms monooxide, that is, lithium will form Li2O, whereas the sodium will form peroxide Na2O2, whereas all other, that is, whether it be potassium, whether it be rubidium, whether it be cesium, they will all form superoxides, that is KO2, RbO2, CS2, and in all these oxides, that is, all the oxides, the oxidation state of the alkali metal, whether it be monoxide, whether it be just monoxide, whether it be peroxide, or whether it be superoxide, it is always going to be +1. Lithium shows exceptional behavior on reacting directly with nitrogen to form nitride. That is, lithium is the only one in the entire alkali metal which directly reacts with nitrogen to form nitride, and it also forms hydrated salt, that is LiCl.2H2O. It was LiCl.2H2O, right? Yeah, LiCl.2H2O. No other alkali metal shows these two properties. Then, because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Why are they kept in kerosene oil? Because alkali metals have very high reactivity towards air and water. What is the oxidation state of K in KO2? It is always going to be +1 because it's a superoxide. And what will be oxygen's that is, here oxygen, the oxidation state of oxygen is going to be -2. Over here the oxidation state of oxygen in peroxide is going to be -1, and over here in superoxide it is going to be -1/2. And for all the alkali metals it is going to remain +1. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. So, very important statement. That is, for air we saw monoxide, peroxide, and superoxide. Now for water, alkali metals react with water to form hydroxide and dihydrogen. Hydroxide and dihydrogen. So if M is an alkali metal, then M reacts with H2O to form 2M plus 2OH plus H2. So it forms hydroxide and dihydrogen. It may be noted that although lithium has the most electro-E0 value, that is, has the most negative E0 value, its reaction with water is less vigorous than that of sodium, which has the least E0 value. So lithium has the most negative E0 value, therefore it is a very good reducing agent, whereas sodium has the least negative E0 value, and it reacts with water vigorously. The behavior of lithium is attributed to its small size and very high. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals react explosively with water. They also react with proton donors such as alkynes, alcohol, and gaseous ammonia. So when it comes to water, the alkali metals form hydroxide and dihydrogen, which is very important to remember. Then it has to be noted that lithium has the most negative E0 value. Its reaction with water is less vigorous than that of sodium, and sodium has the least negative E0 value among the alkali metals. All other alkali metals react explosively with water, and the behavior of lithium, wherein it is not that aggressively reacting with water, vigorously reacting with water, is due to its very small size, and very high hydration enthalpy or hydration energy. And all other alkali metals, they also react with proton donors such as alkynes, alcohol, and the gaseous ammonia. Then reactivity towards dihydrogen. That is, the alkali metals react with dihydrogen at 673 Kelvin, and lithium reacts at 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting point. So what happens with reaction with dihydrogen? That is, the alkali metals react with dihydrogen at 673 Kelvin. The only exception is lithium, which reacts with dihydrogen at 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. So 2M plus H minus. So 2M plus H2 gives 2M plus H minus. They are all solid ionic solids, and they all have very high melting points. They all have high melting points. Hydrides, all the alkali metal hydrides have a high melting point. Now, reactivity towards halogen, the alkali metals react vigorously with halogen to form ionic halides M plus X minus. However, lithium halides are somewhat covalent. Why are lithium halides covalent? Because they have very low size and very high polarization capability because of their very small size, not low size, I'm really sorry. They have very small size. Because of their very small size, they are able to distort the anion's electron cloud, because the anion has a very big size. So very small size, they have very high tendency to distort the electron cloud, or you can say very high polarizability. That is the distortion of electron cloud of the anion by the cation is called as polarization. So they have very high polarizing power or polarizability, and because of this, they distort the electron cloud around the negative halide ion. And since anion with large size can easily be distorted among halides, lithium iodide is the most covalent in nature. So among halides, lithium iodide is the most covalent in nature. Now, reducing nature. Alkali metals are strong reducing agent, but lithium has the most negative E naught value, and it is the strongest reducing agent. And most and the sodium is the least powerful reducing agent. The standard electrode potential E naught values which measure the reducing power represents the overall change. That is M solid to M gas, sublimation enthalpy, M gas to M plus plus electron minus, that is removing one electron, ionization enthalpy. Then that is M plus plus H2O gives M plus aqueous, that is hydration enthalpy. How well the cations they react with water, that is they become aqueous to give ions. Hydration enthalpy. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E naught value and its high reducing power. So why is lithium very highly reducing agent? This is because it has the highest hydration enthalpy, which accounts for its high E naught value, and it has high hydration enthalpy because of its small size and high E naught value and high reducing power. Here the E naught values are given. Most negative is lithium, then greater than sodium, greater than I minus, greater than Ag, greater than Cl minus. Look which is the most negative, and then arrange it accordingly. If values are given, then they will be given. They won't ask you to memorize these things. Solutions in liquid ammonia. Alkali metals dissolve in liquid ammonia to give deep blue solution. Why? This is because of the ammoniated electron. That is alkali metal dissolve in liquid ammonia to give deep blue solutions which are conducting in nature. That is M X plus Y NH3 gives M NH3 X plus E NH3 Y minus. So the blue color of the solution is due to ammoniated electron which absorbs the energy in the visible region of light and therefore or thus imparts blue color to the solution. The solutions are paramagnetic. Paramagnetic, that is they have unpaired electrons, and on standing slowly they liberate hydrogen resulting in the formation of amide. Here where Am denotes solution in ammonia, in concentrated solution the blue color changes to bronze color and it becomes diamagnetic, that is paired electrons. So solutions in liquid ammonia, that is when alkali metals are the alkali metals dissolve in liquid ammonia, then they give us deep blue solution. Why do they give us deep blue solution? This is because of the ammoniated electron which absorbs energy in the visible region of light and it imparts blue color to the solution. The solutions are paramagnetic, that is they contain unpaired electrons, and on standing slowly they liberate hydrogen resulting in the formation of amide. If you leave the solution stranded, then it will on standing for a long time it is going to become amide, that is it will liberate hydrogen, that is and it will become formation of amide will take place, and in concentrated solution the blue color will change to bronze color and become diamagnetic. Uses. Lithium is used to make useful alloys. For example, with lead, it is used to make white metal bearings for motor engines. With aluminium, it is used to make aircraft parts. With magnesium, it is used to make armor plates. It is used in thermonuclear reactions. Okay. So now let's see the uses. What are the uses of lithium? Lithium is used in thermonuclear reactions. Then lithium is used along with aluminium to make aircraft parts. Lithium is used to make useful alloys. Along with lead, lithium is used to make white metal bearings for motor engines. Then with magnesium, lithium is used to make armor plates. Then lithium is also used in electrochemical cells, to make electrochemical cells. Now sodium. Sodium is used to make sodium lead alloy, which was earlier used in knocking. That is needed to make PbEt4 and PbMe4. These were the organo-lead compounds which were earlier used in anti-knock additives to petrol, but nowadays we use lead-free petrol. Then liquid sodium metals were used as coolant in fast breeder nuclear reaction. Liquid sodium metal is used in coolant in fast breeder nuclear reaction. Potassium has a vital role in our biological system. Potassium chloride is used as a fertilizer. Then potassium hydroxide is used in the manufacture of soft soap, and it is also an excellent absorbent of carbon dioxide. So about potassium, that is, potassium has a vital role in our biological system. Potassium chloride is used as a fertilizer, and potassium hydroxide is used in the manufacture of soft soap. Potassium chloride is um, used as an excellent fertilizer, and potassium hydroxide is used in the manufacture of soft soap. The same potassium hydroxide is also used, it also makes an excellent absorbent on carbon dioxide. Then cesium is used in devising photoelectric cells. Where is cesium used? Cesium is used in devising photoelectric cells. We saw na potassium and cesium, they are very useful in photoelectric cells. This is because with very little energy they absorb that light energy, or when light is when light shines on them, then they absorb that light energy, and they lose one electron very readily. General characteristics of the compounds of alkali metals, that is, all the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of the compounds are discussed here. Firstly, oxides and hydroxides. So on combustion with air, lithium forms mainly the oxide Li2O, plus it also some peroxide Li2O2. But monoxide, that is oxide Li2O, that is lithium is the only one that can form that. Then sodium forms peroxide Na2O2, but it can also form some superoxide, that is NaO2. Then whilst potassium, rubidium and cesium, they only form superoxides, that is MO2, where M can be K potassium, then Rb rubidium and Cs cesium. Now under appropriate condition, pure compounds like M2O, M2O2 and MO2 may be prepared. The increasing stability of peroxide or superoxide as the size of the metal ion increases is due to the stabilization of large anions by larger cations, that is through lattice energy effects. This is very important. Again, this point is very important. That is why does the stability of peroxides and superoxides increases as we go down the group. This is because of the stabilization of large anions by larger cations, because as we go down the group, the size, the atomic radii, ionic radii, they all increase, and this is through the lattice energy effect. These oxides are easily hydrolyzed by water to form hydroxides according to the following reactions. So lithium when reacted with water forms 2M plus OH minus. It only gives OH minus. That is, lithium only gives OH minus when reacted with water. That is, lithium oxide when reacted with water or moisture gives only OH minus, whereas peroxide gives OH minus plus peroxide, and superoxide gives OH minus plus peroxide plus oxygen. The oxides and the peroxides are colorless. The oxides and the peroxides are colorless, but the superoxides are either yellow or orange. So the oxides and peroxides are always going to be colorless, but the superoxides are either yellow or orange in color. The superoxides are also paramagnetic, that is sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. Sodium peroxide is widely used as an oxidizing agent in organic chemistry. This is a very chuparustam wala line. The superoxides are also paramagnetic. See? Superoxides are paramagnetic. And why are superoxides paramagnetic? That is, why is KO2 paramagnetic? This is because it has an unpaired electron. Where? In pi star 2p orbital, molecular orbital. Now hydroxides which are obtained by the reaction of the oxide with water are all white crystalline solid. The hydroxides which are obtained, that is lithium, so does not okay, sorry. The hydroxides which are obtained when the oxides of the alkali metals react with water, they are all white crystalline solids, and the alkali metal hydroxides are the strongest of all bases. They dissolve freely in water with evolution of much heat on account of intense hydration. That is, they dissolve easily in water and they give out very much intense. That is very much evolution of heat on account of intense hydration, due to intense hydration. Now halides. The alkali metal halides, that is MX, they are all high melting colorless crystalline solids. They can be prepared by the reaction of appropriate oxide, hydroxide and carbonate with aqueous hydrohalic acid, HX. That is the alkali metal halides, that is MX. That X can be either fluorine, chlorine, bromine or iodine. They are all high melting. They are all colorless crystalline solids. The alkali metal halides MX, where X can be the halogens fluorine, chlorine, bromine, iodine. They are all very high melting and colorless crystalline solids. Colorless crystalline solids, all of them. And they can be prepared by the reaction of appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. How can they be prepared? They can be prepared by the reaction of the appropriate alkali metals, either alkali metal oxide or hydroxide or carbonate with hydrohalic acid, aqueous hydrohalic acid, that is aqueous HX. HX is called aqueous hydrohalic acid, that is any halogen with that is hydrogen HX, hydrohalic acid. All of these halides have very high negative enthalpies of formation, that is delta FH minus values, that is the enthalpy of formation is very high and very highly negative values. For fluorides, it becomes less negative as we go down the group, whilst the reverse is true for chlorides, bromides and iodides. So for fluorides, it is this is also very important point. You have to erase like this. This is the color, right? This is a very important point. ये तो हमेशा का ही है. This always happens. Okay. हाँ ठीक है. See, whether it be alkali metals oxides or hydroxides or carbonates, when we react it with HX, that is hydrohalic acid, then that is we get high melting colorless crystalline solids. Now all of these halides, then we get the halides of these metals, alkyl halides, and sorry, not these alkali metal halides, alkali metal halides, and all of these halides, they have very high negative enthalpy of formation, that is their delta FH minus, that is the enthalpy of formation is very high, highly negative values. For fluoride, they become less negative as we go down the group. So for fluoride, that is, you can say LiCl, then RbCl, CsCl, NaCl, KCl, that is for, arey yaar, what am I doing? Sorry, LiF, RbF, NaF, CSF, KF, these for all the fluorides, the enthalpy of formation it becomes less negative as we go down the group, whilst the reverse is true for the enthalpy of formation for chlorides, bromides and iodides. So if the same I will say for LiCl, RbCl, NaCl or KCl or NABr, RBr and all, then RBBR, KBR, then the reverse is true. That is, as we go down the group for alkaline metal, fluoride, bromides, and iodides, then the enthalpy of formation will become more negative. Whereas for fluoride, it will become less negative. This is very important. It needs to be highlighted more because this is very important. This is very, very important. ये क्या हो जाता है? हाँ, ठीक है. Now, for a given metal, enthalpy of formation always becomes less negative from fluoride to iodide. So, from fluoride to iodide, if we compare it between, that is, fluoride to iodide, then it always becomes less negative. That is, fluoride will have the highest, most negative, and iodide will have less negative. So if we are comparing like LIF, LIBR, LICL, then what LIF will have the most negative enthalpy of formation, and LII, lithium iodide, will have the least. Now, melting and boiling point always follow the trend. That is, fluoride has the highest melting and boiling point, then chloride, then bromide, then iodide. For alkaline metals, all these halides are soluble in water. The low solubility of lithium fluoride in water is due to, that is, all of them are soluble in water, but least soluble is, that is, low solubility of lithium fluoride in water is due to its high lattice enthalpy, whereas the low solubility of cesium iodide is due to its smaller hydration enthalpy of two ions. So lithium fluoride and cesium iodide. Why is lithium fluoride less soluble? This is because of its very high lattice enthalpy. That is why lithium fluoride is less soluble in water. But why is cesium iodide less soluble in water? This is because cesium has the largest size, atomic size, and largest atomic size means lowest hydration enthalpy, and therefore due to its smaller hydration enthalpy of its two ions, cesium iodide is also very less soluble in water. Other halides of lithium are soluble in ethanol, acetone, ethyl acetate, and LiCl is soluble in pyrimidine also. This is also a very important point. That is, lithium fluoride is soluble in pyrimidine also. Now we come to salts of oxoacids. Oxoacids are those in which acidic proton is on a hydroxyl group with an oxo group attached to the same atom, like for example carbonic acid. So what are oxoacids? Oxoacids are those in which the acidic proton on a hydroxyl group, that is, the acidic proton on a hydroxyl group OH with an oxo group attached to the same atom, for example carbonic acid. So double bond O, oxo group, and hydroxyl group OH having a proton, they are attached to the same atom. So let's take carbonic acid, H2CO3. So C, then double bond O, plus you have hydroxyl group OH whole twice. So we get H2CO3. Then similarly sulfuric acid, H2SO4. So you get firstly SO2, S double bond O double, then OH whole twice. So H2SO4. Those are salts of oxoacids. The alkali metal forms salts with all the oxoacids. They are generally soluble in water, and the salts of that is the alkali metal forms salts with all the oxoacids, and the salt of oxoacids of alkali metals are generally thermally stable and soluble in water. They are soluble in water and they are thermally stable. Their carbonates M2CO3 and in most cases hydrogen carbonates NHCO3 are also very highly stable to heat. They are also thermally stable. As the electropositive character increases down the group, the stability of the carbonates and hydrogen carbonate increases. Because the electropositive character increases down the group, the stability of carbonate and hydrogen carbonate increases. What does this mean? This means that cesium carbonate and cesium hydrogen carbonate is going to be most stable than lithium or sodium or potassium and all. So lithium carbonate is not so stable to heat. Lithium being very small size, in being lithium carbonate is not so stable to heat. Why? Because lithium being very small in size polarizes the carbonate ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. So the hydrogen carbonate of lithium does not exist as a solid because it shows the diagonal property to magnesium, right? Ahead you will see that even magnesium hydrogen carbonate does not exist as a solid. Now lithium carbonate is not so stable to heat also because of its very small size polarizes a large carbonate ion, leading to the formation of more stable Li2O and CO2, oxide and carbon dioxide. Anomalous properties of lithium. The anomalous behavior of lithium is due to firstly its exceptionally small size of atom and ion, then secondly the very high polarizability of polarizing power, that is charged by radius ratio. As a result, there is increased covalent character of lithium compounds. We saw that lithium iodide is most covalent halide. Then it is responsible for their solubility in organic solvent. There is increased covalent character of lithium compound which is responsible for their solubility in organic solvents. So because of their very high covalent character, they are soluble in organic solvents. Lithium shows diagonal relationship to magnesium, which has been discussed subsequently. Points of difference between lithium and other alkali metals. That is, lithium is much harder. The melting point and boiling point, which decrease down the group, they are higher than all the other alkali metals. Lithium is least reactive, but it is also the strongest reducing agent among all the alkali metals. On combustion in air, it forms lithium monoxide, which and lithium nitride, that is Li2O and Li3N, which no other alkali metal forms. Then lithium fluoride is deliquescent. What is the meaning of deliquescent? That is, it absorbs moisture and therefore it crystallizes to form a hydrate, that is LiCl.2H2O, whereas no other alkali metal form hydrates. Then lithium hydrogen carbonate is not obtained in solid form, whereas all other alkali hydrogen carbonates are in solid forms. Then lithium, unlike other alkali metals, forms no ethynide on reaction with ethine. That is, all other alkali metals, when they react with ethine, this is another very important point, when they form ethynide, whereas lithium, unlike other alkali metals, does not form ethynide on reaction with ethine. Lithium nitrate, when heated, gives lithium oxide, that is Li2O, whereas other alkali metal nitrates decompose to give the corresponding nitrite. So lithium nitrate. So lithium nitrate is the only one which gives lithium oxide and NO2 and oxygen, whereas all other alkali metals give, that is, all alkali metal nitrates give metal nitrides, their corresponding nitrides, whereas lithium directly gives oxide and alag se it gives nitrogen dioxide and oxygen. Now lithium fluoride and lithium oxide are comparatively much less soluble in water than the corresponding compounds of other alkali metals. Lithium fluoride and lithium oxide, they are much less soluble in water than the other corresponding compounds of other alkali metal. We saw the reason for lithium fluoride, that is, it has very high lattice enthalpy. Okay. Now, points of similarity between lithium and magnesium. We know that lithium shows anomalous properties and it shows diagonal relation as when compared to other alkali metals, and it shows diagonal relationship that with magnesium, that is similar properties to magnesium. Similarity is because particularly striking. It arises because of their similar sizes. That is, atomic radii of lithium is 152 picometer, whereas of magnesium is 160 picometer. Then ionic radii is 76 picometer, whereas that of magnesium is 72 picometer. The main points of similarity between lithium and magnesium are both lithium and magnesium are harder and lighter than other elements in their respective groups. So lithium and magnesium, both of them, they both are much more harder. That is, all other alkali and alkaline earth metals are that is tough to break, that is soft, whereas both of them are harder and they are lighter than other elements in their respective groups. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble and their hydroxides decompose on heating. So lithium and magnesium, they both react slowly with water. Their oxides and hydroxides are much less soluble in water than all other alkaline metals, and their hydroxides decompose on heating. Both form a nitride, Li3n and Mg3n2 by direct combination with nitrogen. Oxides Li2O and Mg2O. Li2O and Mg2O. Sorry, MgO, do not combine with excess oxygen to give any superoxide. So once they are formed, they are formed. They do not combine with excess oxygen to give any superoxide. Carbonates of lithium and magnesium, they decompose easily on heating to form oxides and carbon dioxide. Solid hydrogen carbonates are not formed by both lithium and magnesium. Both lithium chloride and magnesium chloride, they are deliquescent, and they crystallize to form aqueous solution, that is LiCl.2H2O and MgCl2.8H2O, and both lithium chloride and magnesium chloride are soluble in ethanol. Some important compounds of sodium, that is industrially important compounds of sodium, are sodium carbonate, also called as Na2CO3.10H2O, when hydrated forms washing soda. Then sodium hydroxide, NaOH, or caustic soda. Then sodium chloride, also called as common salt or table salt, NaCl. And lastly sodium bicarbonate, NaHCO3, baking powder or baking soda. The large scale production of these compounds and their uses are described below. Sorry, sodium bicarbonate, something else. This is also for limestone and all, na? Yeah, sorry. Sodium carbonate or washing soda, that is Na2CO3.10H2O. Sodium carbonate is generally prepared by Solvay process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, wherein it gets precipitated in the reaction of sodium chloride. So firstly, we take sodium chloride and ammonium hydrogen carbonate, that is NH4. That is firstly, okay. So what happens in Solvay process? In Solvay process, firstly we take ammonia and we pass carbon dioxide, and we react it to dissolve it in water and pass carbon dioxide through it to get ammonium carbonate. Then after getting ammonium carbonate, we again take ammonium carbonate and we dissolve it in water and pass carbon dioxide through it to form ammonium hydrogen carbonate. Then after forming ammonium hydrogen carbonate, we react ammonium hydrogen carbonate with salt to get sodium hydrogen carbonate. This is not washing soda. Sodium hydrogen carbonate and ammonium chloride. So sodium hydrogen low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing carbon dioxide to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equations for the complete process may be written as ammonia dissolved in water, and you pass carbon dioxide to form ammonium carbonate. Then you take ammonium carbonate, you dissolve it in water, then you pass carbon dioxide, you form ammonium hydrogen carbonate. Then you react ammonium hydrogen carbonate with ammonium chloride to form ammonium hydrogen carbonate. You react with sodium chloride to form ammonium chloride and sodium hydrogen carbonate. Then sodium hydrogen carbonate crystal separates, and these are heated to give sodium carbonate. So you take sodium hydrogen carbonate and then you heat it to form sodium carbonate, carbon dioxide and water. In this process, ammonia is recovered when the solution containing ammonium chloride is treated with calcium hydroxide. Then we get calcium chloride as a byproduct, and we get our ammonia back if we want our ammonia back. Then that reaction is also written, that is ammonium chloride on reaction with calcium hydroxide, we get ammonia, calcium chloride and water. It may be mentioned here that Solvay process cannot be extended to potassium. Why? This is because potassium will become manufacture of potassium carbonate can't be done by Solvay process, because potassium carbonate or potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. So we cannot get potassium. So why do we do Solvay process? Solvay process, the main conclusion or the main purpose or principle of Solvay process is that low solubility of sodium hydrogen carbonate. We need to get sodium hydrogen carbonate when we add sodium chloride to ammonium hydrogen carbonate. But the same can't be said for potassium, because potassium hydrogen carbonate has very high solubility, and therefore uh, when we add potassium chloride to ammonium hydrogen carbonate, then the potassium hydrogen carbonate that we will obtain will dissolve, and hence we cannot obtain it. And if we cannot, that is, it won't get crystallized and it won't get separated basically. So therefore, if we don't get potassium hydrogen carbonate, then we can't get potassium carbonate by heating potassium hydrogen carbonate. Therefore, we cannot manufacture potassium carbonate by the process of Solvay process. It may be properties. Sodium carbonate is white crystalline solid. It exists as a decahydrate. So we saw that all the carbonates and hydrogen carbonates, except for lithium, they are all white crystalline solids. So sodium carbonate is a white crystalline solid. It exists as a decahydrate, Na2CO3.10H2O. It is when it exists as a decahydrate, then it is called as washing soda. It is readily soluble in water. On heating, the decahydrate loses its water, that is 10H2O. It loses its water to form monohydrate. So 9 water molecules are lost. But if we heat it above 373 Kelvin, then the monohydrate also, it loses the monohydrate also, and it becomes completely anhydrous and changes to a white powder, and this white powder is called as soda ash. That is, it changes to only Na2CO3. So Na2CO3.10H2O decahydrate or washing soda, when heated below 373 Kelvin, then it forms sodium carbonate .H2O, that is, it forms a monohydrate, and 9H2O it gives out. But if we heat it above 373 Kelvin, then it forms a white powder which is called as soda ash, and it loses the water also, and it becomes completely anhydrous. Now, carbonate part of the sodium carbonate gets hydrolyzed by water to form an alkaline solution. The carbonate part of sodium carbonate, that is CO3 2-, it gets hydrolyzed by water to form an alkaline solution, HCO3- and OH-. It is used in water. What is the uses of washing soda? It is used in softening of water, laundering and cleaning. It is used in the manufacture of glass, soap, borax and caustic soda. Caustic soda NaOH, also in the glass, soap, borax. It is used in paper, paints and textile industry. It is used as a very important laboratory reagent for qualitative and quantitative analysis. What are the importance of washing soda? That is, it is used in water softening, laundering and cleaning. It is used in the manufacture of glass, soap, borax and caustic soda NaOH. It is used in paper, paints and textile industries, and it is an important laboratory reagent both in qualitative and quantitative analysis. Now, sodium chloride NaCl. Sodium chloride or NaCl is the most abundant source of sodium chloride in seawater. It contains 2.7 to 2.9% by mass of the salt in tropical countries like India. So sodium chloride NaCl is most abundant source of sodium chloride. That is the most abundant source is seawater. It contains 2.7 to 2.9% by mass of the salt. In tropical countries like India, common salt is generally obtained by the evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. And crude sodium chloride, generally obtained by the crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. So crude sodium chloride, that is, it contains impurities. It is basically obtained by the evaporation of brine solution. And what are the impurities that crude sodium chloride contains? It contains sodium sulfate, calcium sulfate. Okay, so there is no magnesium sulfate. Okay, it contains sodium sulfate, calcium chloride and magnesium chloride. What do we want? We want sodium chloride. What are the impurities? Magnesium and calcium chloride, and sodium and calcium sulfate. Magnesium and calcium chloride and sodium and calcium sulfate. Now, calcium chloride CaCl2, that is calcium chloride and magnesium chloride, they are impurities because they are deliquescent, that is they absorb moisture easily from atmosphere. So to obtain pure sodium chloride, fruit salt is dissolved in minimum amount of water and then filtered to remove the insoluble impurities. What do we do to obtain pure sodium chloride? We dissolve it in minimum amount of water and then we filter out the impurities. The solution is then saturated with hydrogen chloride, that is HCl gas. How is it saturated? It is saturated by HCl gas. Crystals of pure sodium chloride separate out. By this process, what happens? Crystals of pure sodium chloride separate out. Calcium and magnesium chloride, which are more soluble than sodium chloride, they remain in the solution. Because calcium and magnesium chloride, CaCl2 and MgCl2, they are both more soluble than sodium chloride, they remain in the solution. Sodium chloride melts at 1081, that is 1081 Kelvin, and it has a solubility of 36 gram and 100 gram of water at 273 Kelvin. The solubility does not increase appreciably with the increase in temperature. The solubility of sodium chloride does not increase appreciably with the increase in temperature. What are the uses? It is used as a common salt or table salt for domestic purpose. Oh, by the way, sodium hydrogen carbonate is in fact used is baking soda, baking powder. I confused it with some other compound. Uses. It is used as a common salt or table salt for domestic purpose, and it is used in the preparation of sodium peroxide Na2O2, caustic soda, sodium hydroxide NaOH, and sodium carbonate Na2CO3. Sodium hydroxide or caustic soda. Sodium hydroxide are generally prepared commercially by the electrolysis of sodium chloride in Kastner-Kellner cell. What happens? You take NaCl sodium chloride and Kastner-Kellner cell, that is a brine solution, is electrolyzed by using mercury cathode and carbon anode. So you take a brine solution, that is NaCl solution, in a Kastner-Kellner cell having mercury cathode and carbon anode, and then the sodium metal is discharged at the cathode. Na plus, that is cation cathode, and ion anode. So sodium metal Na plus is discharged at the cathode and it combines with mercury to form sodium amalgam, and chlorine gas is evolved at the anode. So the amalgam, that is sodium and mercury, it is treated with water to give sodium hydroxide and hydrogen gas. This is how you obtain caustic soda or sodium hydroxide. What is sodium hydroxide? It is white translucent solid. It melts at 591 Kelvin, whereas your sodium chloride was melting at 1081 Kelvin. Then it is readily soluble in water to give a strong alkaline solution. Crystals of sodium hydroxide are deliquescent, that is they absorb moisture. The sodium hydroxide solution at the surface reacts with the carbon dioxide in the atmosphere to form sodium carbonate. The sodium hydroxide solution, which is at the surface, it reacts with carbon dioxide in the atmosphere to form sodium carbonate. Then it is used in the manufacture of soap, paper, artificial silk. It is used in the mercerizing of cotton fabrics in textile industry. It is used in the purification of bauxite. It is used in petroleum refining. It is used for the preparation of pure fat and oil, and it is also used as a laboratory reagent. So what is it used for? Used for the manufacture of soap, paper, artificial silk, number of chemicals, used in petroleum refining, used in the purification of bauxite. It is used in the mercerizing of cotton in textile industries. And it is used for the preparation of pure fats and oils, and it is used as a laboratory reagent. Then sodium hydrogen carbonate, baking soda. NaHCO3, that is sodium hydrogen carbonate, is also known as baking soda. Why? Because it decomposes on heating to generate bubbles of carbon dioxide, and it leaves holes in cakes, pastries, and makes them light and fluffy, bouncy. That is. Then sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. How is sodium hydrogen carbonate made? Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate Na2CO3 with carbon dioxide. And the white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. By Solvay process also you can directly get sodium hydrogen carbonate. Like Na2CO3 with H2 and CO2 you will get it. This is another way. Sodium hydrogen carbonate is mild antiseptic for skin infection, and it is used in extinguisher. So it is used in fire extinguisher. It is a mild antiseptic for skin infection. Also, you know, ant bite and all, they always say to apply some baking soda. It actually helps. It is the um, itching and all you don't feel. And then most important, use as baking soda, that is for to make the cakes and the pastries and all fluffier and to make them rise. Biological importance of sodium and potassium, that is a typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, only 5 gram of iron and 0.06 gram of copper. Sodium ions, that is you will find more sodium in extracellular fluid and you will find more potassium in intracellular fluid, which is the most important part. That is the most abundant cation in extracellular fluid is sodium. The most abundant cation in intracellular fluid inside the cell is potassium. So sodium ions are found primarily on the outside of cells located in blood plasma. You know your blood is made up of plasma plus WBC, RBC platelets, and major part of it is plasma. So in the interstitial fluid which surrounds the and also the interstitial or tissue fluid which surrounds the cells, these ions participate in the transmission of nerve signal, that is your transmission of nerve signal, the saltatory movement that you say. It is due to the that is also help in regulating flow of water across cell membranes, that is wherever there is active transport, K plus Na plus pump is there, in the transport of sugars, amino acids and amino acids into the cells. So higher concentration, low concentration, maintaining ionic balance and osmotic balance, osmoregulation and all, sodium and potassium ions, they are very useful. All sodium and potassium, although so similar chemically, they differ quantitatively in their ability to penetrate cell membrane, in their transport mechanism and in their efficacy to activate enzymes. So even though they are so similar, sodium and potassium, both of them, chemically, they differ quantitatively in their ability to penetrate the cell membrane, transport mechanism and in their efficiency to activate enzyme. Thus, potassium ions are most abundant cations within the cell fluid, that is intracellular fluid. Highest found cation is potassium, where they activate many enzymes. They participate in the oxidation of glucose to produce ATP, and with sodium they are responsible for the transmission of nerve signals. So that is potassium ion, they activate many enzymes, they participate in the oxidation of glucose to produce ATP, and with sodium they are responsible for transmission of nerve signal. There is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of cell membrane. That is, as a typical example, the blood plasma, that is sodium present, there is 143, that is in blood plasma outside the cell extracellular fluid, 143 millimoles per liter sodium ions are present, whereas potassium level is only 5 millimoles per liter outside the cell. Within the red blood cell, whereas they change to 10 millimoles of sodium ion, whereas 105 millimoles of potassium ion. So these ionic gradient demonstrate that there is a discriminatory mechanism, and this is called as sodium potassium pump, which operates across the cell membrane, which consumes more than 1/3 of the ATP by a resting animal and 15 kg per 24 hours in a resting human. So I thought like I can finish it in one go, but I think group 2 elements will do it in another video. Revision, so this will be revision of entire group 1 elements, because group 2 elements again it is a lot. So thank you.